Morning, guys. My name is Stephen Cohen, and today I'm going to be presenting underwater direction finding using a single hydrophone. First, I'd like to thank my mentor, Dr. George, as well as NSF for sponsoring this 2026 REU. Also want to thank FAU for hosting the experience and CAAI Lab for their collaboration. For underwater transmissions, we typically rely on acoustic waves to send our bits of information and communication. Typically, you would have a transmitter, something like the submarine here, that sends off a signal. Eventually, you have a receiver, like the boat, for example, that picks it up. Now, sending and receiving a signal is really only part of the equation. If you want to find which direction that came from, that's a whole other problem in itself. Traditionally, the solution to these problems are large arrays of sensors, which you can see here is called a towed linear array. These things are definitely good, they're capable, but they start to present their own problems in themselves. For one, you might ask, how am I going to tow this giant thing through the water? You might ask, how much power would this take to turn on? Or you might wonder, how much is it going to cost? These are all perfectly valid questions, and the point is, we need better answers for these solutions at varying scales. And that's what brings us to the motivating question for this research. Instead of having this large array of hydrophones, can we extract that same directional information from just a single hydrophone? So this research looks to recreate a project about a device called Amulet. Amulet is a 3D printed structure that takes inspiration from both nature and physics. When you look in nature, we have these seashells that have really uniquely spatial geometry, as well as trapped cavities of air. Now, physics tells us that air is a high impedance material to these underwater acoustic waves, while simultaneously, the plastic that the 3D printer spit out is a low impedance. That means that when you take this structure and you put it underwater, you create these invisible paths for the acoustic signals to travel through the plastic PLA, while simultaneously creating these high impedance center cavities for the signals to come in and bounce around that internal structure, as well as a third path, which just directly goes through the whole thing eventually. So what you're seeing is that one wave has now been turned into three uniquely time-delayed signatures. The signal that you see, wave A, is still wave A, just split into three different waves now. Again, what we've done is we've taken one signal and we've turned it into three. And instead of needing that large array that you saw in the last slide, we've shrunk this down into a small form factor needing just a single hydrophone and some 3D printed plastic parts. But we're not done. We have three digital signals, and now we need to convert that into a known direction. Before I get too far ahead of myself, I want to explain how I get any of this to work and how we get those signals in the first place. So this is my test bed here. Starting off in the corner, I will use two Aquarian AS1 hydrophones. One is going to be the transmitter, and one is going to be the receiver. The receiver has the Amulet wrapped on there so that we can explore this sort of spatial geometry. These are powered by our 120-volt DC supply and then fine-tuned with amplifiers. This signal chain goes up to our SDRs, where you have one for the transmitter and you have one for the receiver. These loop back into the switchboard, where I have an Ethernet connected to my Linux laptop, and I can interface with these signals through GNU Radio. Coming on over here, this was one of the most complicated parts of my project, definitely the most time-consuming, was getting these 3D printed parts all custom made, which had to be made in Blender, prepped in Orca Slicer, printed, installed, and then see where I made mistakes so that I could do it again. What was done specifically, you can see the brackets for support, the 4:1 gear ratio, the pinion, the sleeves for the rod, the wires, the screw mounts, all had to be perfected before I could actually begin the calibration process. The Amulet itself was, of course, 3D printed as well. Interestingly, this was done with 100% infill, which allowed me to avoid any sort of waterproof coating on the Amulet and stayed completely dry for our hourly testing. Of course, a custom 3D bracket was needed here as well to prevent the wire from any sort of turning or slippage during the calibration stage. All of this is so that I can rotate those gears here, controlled by this Teensy 3.2. The teensy has an Arduino script, which is uploaded with this micro USB to my laptop, and then powers this motor device and a 12-volt supply so that I can actually rotate the system and begin calibrating the device. So now that you see how the setup actually works, we can go over the processing pipeline. There's a lot here, so I want to go through just this getting signal A. When we send signal A through the water, it eventually hits our structure. This is going to create those 3 waves that I talked about earlier. From here, we can start to get a little bit more technical and call that signal Y of t. Y of t is going to be comprised of 3 different things. First is going to be our transmitted signal, X of t, convolved with the multipath of t, convolved with the signature of the amulet at a specific angle. A little more detail of the multipath is that this can be modeled as a delta function, where you have time delayed by tau, and tau is just the propagation delay through water. Eventually, the point of doing this is so that we can get these values as our calibrated directional signatures. This is what's going to be our set of reference angles, where we compare our known angles against unknown angles. So now that we have this, we do have signal A from a confirmed direction. What do we do when we want to find unknown A? We run the pipeline again. We get the signal, but this time, instead of saving it to our directional library, we compare it to our directional library. Over here, I'm able to find the maximum correlating values to this unknown and known signal and estimate a specific direction of arrival. So this is going to show you how I get signal A, and basically what you would do if you want to get signal B, you'd stop here, rotate the structure, and then repeat again. But let me go ahead and jump ahead and show you what it looks like when you scale up to get 400 angles. So these are the results from a test I did with a full 360-degree sweep. Our known angles are going to be our x-axis, and then our unknown angles, the ones that we're trying to find the angles for, are our y-axis. Good news is, when you look at this chart, this is exactly what you want to see for these results. What I'm showing is a correlating value starting at 0 to 1 and color-coded. This darker color is just background noise, low correlation, while this bright yellow represents that each angle found a positive correlation to our existing library, showing positive results. Specifically, the 6.5 directional accuracy shows that we found a little more than 2 times our maximum, we found 2 times our 2 times the maximum correct angle compared to any of our wrong diagonal angles. Essentially, what these results are showing is that this metastructure and this processing pipeline produce repeatable directional signatures. Now, as promising as these results are, it's really important to remember that this is just a reproduction in a very early stage controlled testbed environment. There's a lot of future work that could be done that opens up possibilities into exploring different types of metastructures so that we could find more optimal ways of direction finding within the physical structure itself. Other optimizations exist in the processing pipeline itself, where you can have a moving transmitter and a moving receiver to actually deploy these systems, potentially putting them on underwater autonomous vehicles. And then a third option, which is outside the realm of direction finding entirely, is for communications. Theoretically, these physical structures have a unique geometry which can encode that signal and then send it in a secure encoded communications. Overall, these results really open up a lot of several promising possibilities for future work. For me, the key takeaway in all this is just how much inspiration nature can provide us for these solutions in engineering, but also for interdisciplinary research to give us the actual tools needed to put these systems into practical real-world applications. I just want to thank you all for your time, and I'm happy to answer questions later.